It was asked in the break here, from lecture 2A to lecture 2B, what these things represent in this equation here, first of all. And what I explained in the break was that we can pretend we've got two masses, M1 and M2, say. Maybe they could be the Earth and the Sun. And r is the distance between them, essentially between their centers, which in astronomy is about 93 million miles. I forget how many kilometers it is. F is the size of the gravitational force, say, of the Sun on the Earth, and vice versa, actually. K is the constant of proportionality. Its value is mysterious, though it does depend on M1 and M2. In fact, it's directly proportional to M1 and M2 by some other mysterious constant of proportionality. I was also asked about the simple interest, just confirming again that I is a money amount, P is a money amount, R is an interest rate, and T is a time. So for example, if R is 2% per year, you'd write it as 0.02 in using the equation. If you leave the money in there for, say, 10 years, and the units there do need to match in order to use the equation, and the amount of money you start with is $1,000. Oops, that's P, sorry. $1,000, then I is going to be PRT, $1,000 times 0.02 times 10, and what is that going to be, 200? Yeah, $200 of interest over those 10 years. Double check my mental arithmetic if you want. Yep, okay. So that's how you use that equation. Again, for bank accounts, you only earn simple interest during each interest earning period, which in the US here at least is every quarter, every 3 months. And then you have to use compound interest beyond that. I've got a bunch of problem solving things with direct proportionalities. I think we can do these really quick, so let's go ahead and do these. If y is directly proportional to x, and y equals 8 when x is 4, what is the value of y when x is 9? Right? This could be a quiz problem next week, right? What do? You need to use the direct proportionality equation, y equals kx for some k. I won't bother writing f of x here. You don't need to write f of x to solve this problem. The given information will help you solve for k. Y is 8 when x is 4. Plug in y equals 8 and x equals 4. Solve for k. K is going to be 8 divided by 4, 2. Then use k. So y is 2x. Okay, now I'll go ahead and use function notation. So, what is y when x is 9? Y equals f of 9 is 2 times 9 is 18. Here I'm talking about a general y for an arbitrary x. Here I'm talking about a specific y when x is 9. So technically these y's are inconsistent with symbols, but you're okay with that? Next one. If y is directly proportional to x squared, and y equals 8 when x is 4, what is the value when x is of y when x is 9? So now y would be k times x squared. 8 would equal k times 4 squared, which is 16k. Solve for k. K would be 8 divided by 16, or 1/2 for the second problem. So the function would be f of x equals 1/2 x. And when x is 9, you get 1/2 times 9, 9 halves, or 4.5. Next one.
Wait, can we pause?
Maybe I'll just read the next, start reading the next one. Next one, we're looking at when y is proportional to x to the 1/2.
You forgot to square x, didn't you?
Did I forget to square x? Thank
Yeah.
you. There's my, is that my first mistake or my second mistake? I forgot. I'm trying to go too fast here. 81 halves, which is 40.5. Thank you very much. I think that's my second mistake. Well, first mistake in this part of the lecture. I do go too fast sometimes, okay? I get ahead of myself. Y is directly proportional to x to the 1/2. X to the 1/2, by definition, is the square root of x. It's just an alternative symbol for it. That is a good idea because it's consistent with properties of exponents. Go ahead and put either an x to 1/2 or a square root of x here. I'll go ahead and put a square root of x. So I pick nice numbers here. I get the square root of 4 here now, which is 2. So k is 8 divided by 2, which is 4. And now I'm thinking about not making the same mistake as before. This is going to be 4 square root of x. What's f of 9? I picked a nice number there. 4 times square root of 9 is 4 times 3 is 12. Y is directly proportional to x to the negative 1 power. X to the negative 1 power, by definition, is 1 over x, the reciprocal of x, the multiplicative inverse of x. What you multiply x by to get 1. That's what it is. It's nothing magic there. It's done. This is just shorthand notation for that. It's done so that the properties of excellence still work. And in calculus, actually, it's pretty nice to have these functions in terms of exponents. It's going to make something called the power rule much easier to use. K times x to the negative 1, or if you prefer, k over x. Y is still 8 when x is 4, so we get k over 4. So k is 8 times 4, it's 32. So the function's actually f of x equals 32 over x. So f of 9 is 32 over 9. Which, as a decimal, is 3.5 repeating.
Yes.
In this situation, number 4 here, it's actually more common to say y is inversely proportional to x. That's a more common way to describe it. Okay, now we're going to talk about linear functions in general. Here's the general formula. Y equals f of x equals m times x plus b, or just mx plus b. M is, as you know, called the slope or the rate of change. B is called the y-intercept. Actually, the terminology for B could be a little confusing. You know, is the number B the y-intercept, or is the point where you intersect the y-axis the y-intercept? The point, if B is the value of y where you intersect the y-intercept, the point would be 0b. So is B itself the y-intercept, or is that point the y-intercept? You can say it either way. It's not a big deal. Got a couple fundamental properties. B is the initial value of the function. It is the output when the input equals 0. I'm using the phrase initial value because that's a common application. Sometimes x is time, and in that case, you maybe be more likely to call it t. And the initial value is the value of the function at time 0, initial value. But you can still use the phrase initial value even if x is like the number of widgets made in a factory. What's a widget? Anybody know what a widget is? A widget is just just a generic word that means just anything that you might manufacture. It could be anything. Okay. It's a It's a nonsense word, so to speak, representing anything you might want to make in a factory. If x is the number of widgets you make, x equals 0, means making 0 widgets, you might still have a cost, because you still own a building, for example, the factory. So that would be the initial cost when you make 0 widgets, though there's not a time factor involved. Just plug in x equal to 0 to see this. There you go. Fundamental property number 2 is already mentioned, just like with direct proportionalities. M is the rate of change of y with respect to x, and it's also called the slope of the graph. We called it k before, but now we're calling it m. We could have called it m before. Don't let the change of letters confuse you. It's not a big deal. What matters is the ideas, not the notation used as far as actual letters picked. I mean, the notation is helpful once you understand it, though it is a cause for confusion for me. Once again, we can do a calculation to confirm this fundamental property 2 that is ultimately going to calculate delta y over delta x. That's where I made my mistake in lecture 1. I forgot to subtract the f of x, which I call lecture 2a. Here's the calculation. This is something I could put on a quiz or a test. This is something you should be able to do both in the abstract and for a particular example. Go ahead and write it down, but then think. Delta y is the change in y when x changes. When the input changes by some amount, the output is going to change by some amount. It's this difference. There's the initial output. Here's the new output. New minus old, you might say. Then use the formula for the function, mx plus b. When you see f of x plus delta x, take that entire expression, x plus delta x, plug it in place of x way at the top. Put the answer there. This is m times x plus delta x. Now I put the dot in there to emphasize the time, but I didn't have to. If it was just next to this, you should understand it in times. Plus b minus f of x. This entire thing, you use parentheses here. A very common thing to forget is the parentheses here. You need to do that because you can see that the minus sign gets distributed because it's really adding negative 1, so the negative 1 would get distributed through the parentheses. Distribute the m through this parentheses, m times x, m times delta x, get added. Then m times b, and I guess I kind of skipped a step here. The m times b's get canceled. That was the step I skipped. Maybe I should try that. Well, it's a lot to write. We find just writing it on your own, maybe, or just making a note to yourself. And going from here to here, I really did a couple steps. One of which included canceling the m times b, mb. One mb coming from, oh, excuse me, just b's, sorry. One b coming from here and one minus b coming from here. I guess, I mean, you could think of it. It's simple enough you could think of the reason canceling right away, I guess. So if you now divide both sides by delta x, you see that delta y over delta x, rise or run, simplifies to m, the slope, when you're not dividing by 0, as long as there is some change in x. And these are abstract things that we're doing here, which is what makes them tough to follow, which means you need to have the concepts in your mind clearly. This is a difficult thing for me because it's abstract. But it's something worthwhile to look at, to understand things more deeply. Can I clarify anything on the slide? Mm-hmm.
Where did the second parentheses come from, the m times x plus b?
Right there?
Yeah.
That's because I'm subtracting f of x. F of x is the output of the function when the input is x. It's the quantity mx plus b. So I'm subtracting that entire thing. Okay? It does represent a single number, but it's a single number with two terms that are being added. I need to subtract the whole thing, and that's a common mistake I mentioned a few minutes ago. If you don't put the parentheses here, you would just think, oh, I just subtract mx and then I add b, but that's not the case. You subtract mx and you subtract b. That's why it's important to be real careful in those situations. What about the x-intercept? We talked about the y-intercept, that was b. What about the x-intercept? How do you find x-intercepts in general? Can you describe it in a general sense when you're just talking about an arbitrary function f of x?
Set y to 0.
Yeah, set y equal to 0 and solve for x. It's an equation to solve. Set f of x equal to 0 or y equal to 0 and solve for x. With linear functions, it's as simple as it can get. What would be the first step? Subtract b from both sides. Why? Because we're trying to isolate x. If you subtract b from the left side, you cancel the b's. Subtract b from the right, 0 minus b is negative b. That's what you get. Now, assuming m is non-zero at least, divide both sides by m. You get this as long as m is non-zero. Can't divide by 0. There's a unique solution as long as m is non-zero. What if m is 0? If m is 0, that would be undefined, that expression, but the function itself would be a horizontal line. And would either not even touch the x-axis or would be the x-axis. So there'd either be no zeros of the functions, no x-intercepts, or infinitely many when m is 0. This represents what? It represents the value of the input for which the output of the function is 0. The value of x for which y is 0. And that's often important, okay? We will look at plenty of applications of solving equations, finding the value of x, or values in general, where f of x gives you output of 0. Lots and lots of applications of solving equations. X-intercepts are also called zeros or roots of the function. And again, for linear functions with non-zero slope, you have one x-intercept, one zero, or one root. A little confusing to call it a zero, right? Because it's not the number 0 in general. A zero of a function is a value of x that makes the function output 0. X itself is not necessarily 0. Or we call it a zero of the function, or a root of the function. Root makes you think square roots or cube roots or whatever, and that's not always necessarily the case. So it's probably best to call it a 0, but even that's confusing.
Wait, what are you referring to? Sorry. What is it in that second sentence? It is what?
It means the value of x where f of x is 0. The x-intercept. Where does the graph cross the axis? Right there. That value of x, I'll call it x sub 0. That's a root or a 0 of this function. But that number itself may not be 0. It's an input where the output is 0. Because the y-coordinate, the second coordinate of this point is 0. Because it's touching the x-axis. What happens if m is 0? Again, we already mentioned it. This is going to be a rational number, a fraction, a ratio of integers, whole numbers. If m and b are rational, even if m and b are fractions that are rational. Otherwise, it can be irrational. I mean, if m or b is equal to pi, it could be irrational. What would be an application where m or b would be pi or something weird like that? Not many applications. I can't think of any. Most real-life applications deal with rational numbers, however. If, for example, like I mentioned, f of x is the profit or cost, different things it could be, of making x widgets, then the root is the break-even point. Yeah, profit can be positive or negative in a business situation. Profit is the amount of money you take in minus the amount of money you that goes out. Revenue is how much comes in. Expenses is how much goes out. Profit is revenue minus expenses. It's positive, that's good. You're making more money than you're paying out. If it's negative, that's bad. That means you're losing money. Expenses are higher than your revenue. Personal income, you want your income to be higher than your monthly expenses, right? You want to have monthly positive profit. It probably won't happen every month of your life. You know, it's about not happening right now. Probably so. Calculus-related properties of linear functions. Getting close here. Hang on. It's long. That's why we have to break. I'm going to talk a little calculus right now. Calculus-related properties of linear functions. Linear functions are said to be continuous. What does that mean? Got a guess? Keep going. Got to keep going. That's a good guess, I think, but it's not quite what I'm after. There's no breaks in the graph, is what I'm looking for. You can draw the graphs without picking up your writing utensil. By the way, is a vertical line graph of a linear function? No. No. It would fail the vertical line test, which you know functions have to pass, where every vertical line goes through the graph at most once. You might say it's a line with infinite slope, but let's not go there, okay? Anyway, that's just inside. Linear functions are continuous. You can draw the graphs without picking up your writing utensil. No breaks, no holes in the graph. If you've got a hole or a break, it's called a non-continuous function. They're also smooth. What does that mean? It means the graphs don't have any sharp corners or points of infinite slope. You actually can have functions whose graphs have infinite sloping points. The cube root function has a graph that looks about like this, and it turns out that at this one point, it's essentially got infinite slope. But it still passes the vertical line test. Amazing. That is actually not smooth because we don't want infinite slopes. Even though the graph looks smooth, so to speak, in the colloquial sense of the word. They have a constant rate of change, a constant slope, a constant derivative. There's a big word for calculus, derivative. Right? Most nonlinear functions have non-constant slopes. Right? The slope of this is changing every point essentially. Its derivative is not constant. Linear functions, it's constant. Limiting values of the independent variable, limiting values as the independent variable input gets big. I don't know why the quotes didn't go the right way here, by the way. Either positively or negatively, aka goes to plus or minus infinity. What rule are we talking about there? And write it in the board. The limit, Lim, as the input x goes to plus infinity of mx plus b, the output of a linear function at the input x, equals, oh boy, quote unquote, infinity plus infinity if m is positive and minus infinity if m is negative, and I guess it equals b if m equals 0. What in the world? If m is positive, the graph has a positive slope. As x gets big positively, focus on positively, what is the limiting value of y? As x continues to get bigger and bigger, you move further and further to the right, what happens to y? It keeps going up and up as well. There's a bit more precise way to say it. As x gets bigger and bigger without bound, never stopping, going on forever and ever, y will get bigger and bigger without bound. It'll get above any horizontal line you want. No matter what horizontal line I pick, this graph's eventually going to get big enough, bigger, higher than it. Infinity's not a number. I'm kind of treating it like a number here, though. That's the cause of a disconnect for people's minds. But my teacher says infinity is not a number, but he's treating it like a number. What? It's just notation to try to get across an idea. In this case, the idea that I can get higher than any horizontal line, no matter how high it is, by just making x big enough. Can I get above y equals 10 to the millionth power? Really, really huge. Yes, just make x bigger than, I don't know, 10 to the billionth power. Depending on what m is. It's notation for an idea. Now, if I let x go to minus infinity instead, keep going to the left forever and ever, then these signs change, like this. The graph is going down forever and ever when m is positive. When m is 0, then the graph's a horizontal line, and that's why you get b anything at 0. The output is always equal to b. Areas under the graphs, which is important because we talked about that the other day, can be found by geometry because you end up getting trapezoids. Remember the other day we talked about how areas under graphs is important? If the graph is the speed, then the area is the distance traveled. Those areas for linear functions can be found by calculating areas of triangles and trapezoids, which we know formulas for. Here's another property. I'm calling this a non-calculus property. When the slope of the linear function is non-zero, we say it's a one-to-one bounded function. We're going to talk more about what that means on Friday. I got some problem solving with linear functions here. We don't have time for that. You are expected to know how to solve problems like this. They come up in the completion homework, so that's something to work on. I will do at least one of these at the start of class on Friday. See you then.